Good morning, students. Next, we discuss an example based on the conditions of equilibrium. So, our example is if the components parallel to the axis of the force acting on an element of the fluid at the point having the coordinates x, y, z are proportional to y square plus 2 lambda yz plus z square plus 2 mu zx plus x square and x square plus 2 nu xy plus y square. So we are given the components of the force are proportional to these. Means if we take the component of the force along x-axis, x is proportional to this term. If we take the component y along y-axis, that is proportional to this term. And the component along z-axis, that is proportional to this term. We have to show that if the equilibrium is possible, then 2 lambda, 2 mu and 2 nu, each of them are is equal to 1. Now, let us consider capital X, capital Y, capital Z. These are the components of the force along the coordinate axis respectively. Then, by given conditions, X can be written as K into Y square plus 2 lambda YZ plus Z square. Here K is constant of proportionality. Similarly, because Y is proportional to this term, so Y can be written as K into Z square plus 2 mu Zx plus x square, and also Z can be written as K into x square plus 2 nu xy plus y square. Now, because we are given the fluid is in equilibrium, so to use the condition of equilibrium, first of all let us find all the partial derivatives which we require in the equation of equilibrium. So differentiating x partially with respect to y, from here k is constant, derivative of y square is 2y, derivative of 2 lambda yz, that will be 2 lambda z, partial derivative of z square with respect to y, that will be 0. So we have obtained partial derivative of x with respect to y is given by k into 2y plus 2 lambda z. Now differentiating x partially with respect to z, k is constant, derivative of y square will be 0, derivative of 2 lambda yz, that will be 2 lambda y, derivative of z square is 2z. So we get partial derivative of x with respect to z is given by k into 2 lambda y plus 2z. Now let us differentiate y partially with respect to z. From here k is constant, derivative of z square is 2z, derivative of this term is 2 mu x, derivative of x square partially with respect to z is 0. So we get partial derivative of y with respect to z is given by k into 2z plus 2 mu x. Now differentiating y partially with respect to x, we get its derivative which is given by k into 2 mu z plus from here differentiating with respect to x, this will become 2x. So we have obtained the partial derivative of y with respect to x also. Now differentiating z with respect to x partially. So from here k is constant, derivative of x square is 2x, derivative of this term is 2 nu y, derivative of y square partially with respect to x will be 0. So partial derivative of z with respect to x is given by k into 2x plus 2 new y. Now differentiating z partially with respect to y, we get k into 2 new x plus 2y. Now by using the condition of equilibrium, now the condition of equilibrium is given by x into curl y by curl z minus curl z by curl y plus y into curl z by curl x minus curl x by curl z plus z into curl x by curl y minus curl y by curl x is equal to 0. Now let us find all these three expressions one by one, and we will put them in this equation to get the required result. So let us find the first term, x into curl y by curl z minus curl z by curl y. Putting the value of x, curl y by curl z and curl z by curl y here, we get the value of this expression, which is given by 2k square multiplied with the expression y square plus z square into z minus y plus mu x into y square plus z square minus nu into y square plus z square into x plus 2 lambda yz into z minus y plus 2 xyz into lambda mu minus lambda nu. In the same way, you can find these two expressions also, and putting in the equation 1, you will get the expression in this form: x square z minus y square z into lambda plus mu minus 1 plus yz square minus x square y into lambda plus nu minus 1 plus xy square minus xz square into mu plus nu minus 1 is equal to 0. Now, because this equation is true for all x, y, z, so we must have these three terms is equal to 0, means lambda plus mu minus 1 is equal to 0, lambda plus nu minus 1 is equal to 0, and mu plus nu minus 1 is equal to 0. Now, adding the three equations, we get lambda plus mu plus nu is equal to 3 by 2. Now, if we subtract these two equations, we get the value of nu, which is 1 by 2. If we subtract these two equations, we get value of mu, which is 1 by 2. And subtracting these two equations, we get the value of lambda, which is 1 by 2. So we have proved lambda, mu and nu, all the three terms is equal to 1 by 2. So this is how to apply the conditions of equilibrium in our problems. Next, we discuss the topic surface of equal pressures. Surface of equal pressure means a surface through all the points of the fluid at which pressure is same. Such kind of surface is surface of equal pressure. Let us find the equation of surface of equal pressure. For this, let us consider a fluid at rest having the density rho, and let us consider a point having the coordinates x, y, z in the fluid, and suppose P is the pressure at this point. P is the function of x, y and z. Now, if we consider the components of the external force per unit mass, be capital X, capital Y and capital Z, then we have the differential equation of pressure, which we discussed yesterday, that is given by dP is equal to rho into x dx plus y dy plus z dz. Now, integrating this equation, we get P as some function of x, y and z. Now because pressure is same at every point, so we can take P is equal to C. So this equation will become function of x, y, z is equal to C. So this is the equation of the surface at every point of which the pressure is C. For different values of C, we get different surfaces of equal pressures. And for the free surface, C will be 0. So the equation will become function of x, y, z is equal to 0. This is the equation of free surface. Free surface means surface of zero pressure. Now, next we discuss what are lines of force. Lines of force means a curve such that if we draw tangent at every point of this curve, this tangent gives the direction of resultant force at this point. Then we say that this curve is line of force. Now let us find the differential equation of line of force. For this, let us take a fluid, a point having the coordinates x, y, z in the fluid and x, y, z as the components of the resultant force along the coordinate axis. Therefore, direction cosines of line of action of the resultant force, they will be proportional to x, y and z. Also from the geometry, direction cosines of tangent at the point x, y, z are proportional to dx by ds, dy by ds and dz by ds. Now, by definition of line of force, the resultant force acts along this tangent. So we can say that dx by ds, dy by ds and dz by ds, they are proportional to x, y, z. So from here we can say that dx by x is equal to dy upon y is equal to dz upon z. So this gives us the differential equation of lines of force. So we will use these equations in our numerical problems.